Alright, here's Group Carl, and this is totally unscripted. And we've learned that if your brain's not hurting, you're not learning. So here we go.
Hey, question first, guys.
What are the 3 experiments that were the downfall of classical physics?
Somebody name them all, and then we'll talk about them.
Black body, radiation,
photoelectric effect.
Okay.
And then
Anybody else?
relativity. Well, not relativity, but the Michelson and Moore.
making it easier.
Okay. Anybody?
So,
Come on, let's go first.
Okay, I'll start.
okay.
Black body radiation. That was
So do we want to erase everything and then go back and just do the black body? Just put black body up there.
okay. So black body radiation. That's where we got Planck's constant. H equals 6.626 times 10 to the negative 34 joules per second. Okay. Karen, don't forget you have to write this down too. This is your problem.
I know, I will. No big deal.
Okay. So
No big deal, it's just physics.
what exactly did he do to get this again?
I didn't know the answer to all this.
Oh yeah. By classical physics, it should be exponential growth, but through all the calculations, they found it was a hyperbolic.
Wait, calculations of what?
When you do frequency and
Intensity?
the intensity of the
Okay.
Of the light.
yeah. So they're saying that it should be hyperbolic, or they should by their calculations it should be exponential, but it's hyperbolic
So
instead.
classical was
Said this one.
exponential. Okay.
Classical, and then this is where we got quantum physics. This is where we first got the quanta, and from quantum physics. Let's see. Planck thought this was kind of weird, so he found that its energy equals h times f, or wavelength. It's f, right?
Yeah.
Okay. So
I know, it's Planck's constant.
This is
but it
what
doesn't tell us what the black
Max Planck
It's in here.
figured it out. What are you talking about?
Sorry, I was just trying to find out where it is here. Just have a little bit of.
I found it online. I'm actually looking at the graph right now.
Okay.
You want to draw it up there?
So the graph.
Wasn't Planck didn't he completely hate his whole...
All physicists, as soon as they find something, no, seriously, Tony's probably doing problems at home saying, I hate you.
I know, but like he was like really upset about
well,
it.
because he realized that.
Hyperphysics.
Because
Go to the
this
website.
it didn't go do what everybody said.
I didn't.
He was hoping
Yeah.
not to find it.
Well,
He was
because
hoping
it
to
said
find-
that in the book it says like classical wave theory of light would predict that when we increase the intensity of the light striking the cathode, the electrons would come off with greater energy and then blah blah. Let's try that again. The classical wave theory of light would predict that when we increase the intensity of the light striking the cathode, the electrons should come off with greater energy, and the stopping potential should be greater, right? So that's
So-
basically, and then that leads to Planck's constant.
Yeah, because he wanted to. What the classical physics said that it should do this, it should grow exponentially.
But that was the catastrophe, the UV
Yeah.
catastrophe.
Yeah.
But then it turned out, whenever anybody did the experiment, it turned out that their stuff looked like this.
Mm-hmm.
And so, what?
I was just gonna say we should label the axis so that people know what we're talking about.
Intensity.
Because one side is wavelength.
It's like that, right?
No, it's
No.
intensity and frequency.
Okay, because I can read that.
Hey,
I
leave me
is the
alone.
y-axis.
I is?
Yeah.
Yeah,
it's
I is
the
the-
radiation.
Yeah.
And then what's this?
That's
Frequency.
It's frequency.
Yeah, no, yeah, you're right.
Nice writing.
Oh, I have to.
So, oopsie.
Does that make a difference?
But
If it's-
no, it's just that
No,
it
'cause
switches.
frequency
It just
and wavelengths
switches
are
the
the
way
same.
the
Oh,
graph
so
would go.
okay.
So like
Oh.
that's why hers is drawn like this, and the graph's drawn like this. Because
Okay.
you can do it either way.
Yeah.
Yeah.
Yeah. So,
So if you can click on
any more with black body?
See, look, and then it switches.
Well, I was trying to find
If
the
you
book.
change
Does it not
so
talk about it in the
there
book?
was-
I
what do you
swore it talked about it in
mean?
this chapter, didn't it?
It does.
It's just.
See what page it talks about
It's
it.
at the very
It just
beginning.
depends on
Yeah,
what
it's
they
right
look
Well,
there.
I know, I was looking at it, but that's the... I know, that's the Planck's constant, but it doesn't talk about the the rest of it. I thought that was just a photoelectric like talking about here, but it doesn't say black body, does it?
No, it doesn't
Well,
really talk about
it doesn't say anything about Max Planck and what he discovered, because that's what
See, that's
he
what
discovered it through the. It depends on what book you go through. Like some people don't go in through. Yeah. No, he discovered it through black body radiation, but it just depends on what book you look at.
How did he actually do this?
He just took the experimental data and then he did
From
some.
what was the actual experiment? Like not
it was just getting something that was. Okay, you know what Tony was talking about this in class when like you get like an iron and you stick it in a fire, how it changes like colors.
Oh yeah.
Everything does that.
Oh yeah, okay.
Because they all have
The
a
hotter it
certain
is,
heat
They've got
level.
colors.
Yeah.
But at a certain point, it goes back down.
Yeah.
Right.
So, how does that work then? So I mean, because like on a color spectrum, a certain color would actually be at a lower temperature.
Mm-hmm.
Because if you look at it on a color spectrum,
Yeah.
like the hottest it could possibly be,
It turns white.
it turns white. Yeah.
Every
So-
single element, like
I think
metal.
everything does.
Yeah.
Okay.
Yeah, I'm pretty sure.
I'm almost positive that's how it works, but it's not so much. Okay, so
But
what?
it starts emitting a lower frequency at that point.
Yeah,
See, that's
that's what.
okay.
So you got your question
Yeah.
answered.
That was a question. Yeah.
Okay. So do we have anything else to talk about this one, or can we go to a different one?
This is the experiment that figured out that there is actually ether.
There's no ether.
There is no.
There
is
no ether.
Yeah. I was like,
Kidding.
wow.
She altered the problem.
She's like, there is no ether.
Alright, so where do we start here? We had the interferometer thingy, right?
That's a fun word.
Explain this interferometer.
Please. Please explain the physics behind it all.
Well, you see there's this box right here. Honestly, don't know the exact physics of that. All I know is what it's called because that's what it said.
Interferometer, yeah.
Interferometer. But that's what shoots out the little light thingy. Right? Okay, I can't draw,
it is?
so here you go.
Oh, it's almost 10 minutes, guys.
Already?
Yeah.
Okay, we'll keep going.
Okay, so it shoots out the little light beam thing, and it hits this reflector thingy. That's a reflector. Okay. And then it wants to shoot out. Gets sent to reflected this way and this way. So, and then basically,
Oh yeah.
if there is ether,
There should be a.
There should be a time difference.
Yeah.
No.
There should be a gap. Like
Yeah.
where they land.
I thought that's what they found out, that there was a gap.
Yeah, I thought that's what they
They
found
found
out.
that there
No,
was
no, no.
There
ether.
was
No, there was.
No, there was.
Oh,
There
no,
was
you're
no
right.
gap.
You're right.
There was
you're
no
right,
gap.
There was no
There-
gap.
If there was the ether, there would have been a gap.
Yeah.
Oh, okay. So
Because the
there-
ether would have slowed it down.
Yeah.
Or something like that. Yeah, right.
Yeah,
And then
it was
that's
so
when,
fast, it was matter. It was going
relativity
the opposite
came in.
direction, right?
Yeah.
With the gamma.
We were
They-
traveling the opposite
Yeah,
direction of
they
the
looked at
ether.
the world,
Yeah.
and the world was going this way, and they were telling that
They were saying that the world was going like this way,
and
and
it should
the
slow.
ether was going this way.
Like if it was going through the ether,
Kind of like air, like,
like
when you're in a
this
car
one
and you stick
basically-
your hand out.
Yeah.
since
That's
like
what
the
you
Earth's moving that way,
Yeah.
since the
Just
Earth's
keep
like moving that way, like it should take this one longer to get back here to go down to the where it
Where it's
detects
being
the
read.
interference
Right, yeah. As
pattern or
compared
whatever.
to if it.
That's the interferometer right there.
That-
Interferometer.
Yeah.
This is
Yeah.
the interferometer,
Oh, that's
the
interesting.
instrument that shoots out the
Oh, okay.
The
beam.
thingies.
So it splits one beam basically into two.
Then Microsoft
Okay.
actually designed.
Yeah.
So he's like this crazy smart guy that went to school for like ages.
Yeah. This will be us in 80 years. We'll be building interferometers.
So I remember it looked
no.
like
No, baby.
Okay.
if
so
there was ether, like over like time, it would look like the thing shot out this way and made like this triangle thing, and this one. Whoa!
Dance ready.
Sorry.
And this one that shot this way, kind of go all the way this way, and then have to travel back to about here. So if you like laid those out flat, like this one is longer than that one.
Yeah, and then that's.
that one would be longer than
Wait.
that one. Because the triangle is longer.
Yeah, the
Yeah.
triangle is longer, so
Okay.
that one takes longer. Okay, cool.
And then that's when Einstein came up with relativity, or this is one of the main things that made him think of relativity, and that's how we got gamma. Okay, next.
Okay. So basically we have a cathode, we have an anode. This is positively charged, this is negatively charged. And what happens is these light beams right here, it's a monochromatic light and it's going, and this is all enclosed in a glass container. It hits this, and at that point, some electrons. I just need a pen. It's a different color, so it.
Oh, you want
Looking
to.
for that, right?
So at this point, electrons bounce off of it. So you have electrons going in this direction, from towards the anode. And this causes a circuit. When these electrons are lost, the circuit goes around to here. Like this. So it's kind of, I don't know, it's kind of hard to explain.
Well, let's just say the thing that comes out of the photoelectric effect is that particles, or light also has particle.
Right, it's got particle properties.
That's all we've learned from the photoelectric effect. That's all we really
And that's
Well,
why.
yeah. And the basic thing is that what Einstein was talking about was how like low energy photons. Like here on his website is talking about how low energy photons. Like there's no electrons that come off.
Right.
But when the high energy
when it's
photons,
high,
a lot more.
Yeah.
And
And then when it's
That's
highest,
because of B, right?
Of what?
when there's even
that's what it
higher
is, yeah.
energy electrons that come off,
It goes faster, right?
they go even faster than just the high regular one, or the high
Yeah.
ones. So as basically the higher intensity of light that you have going in, the more electrons. Alright.
But didn't we talk about frequency? How like the frequency?
No, it's not the intensity, it's the frequency.
Yeah, it's the frequency. Cause
But the
the
energy-
intensity is the thing that doesn't affect
Yeah,
it.
it
It's the
doesn't affect
wavelength that affects it, and that's the frequency.
Right.
It's interesting because
So wavelength is the frequency?
Yeah. That's what I mean, it's so confusing.
Well, energy
because it's like
is-
there is
well,
no
yeah.
explanation for it, you know?
So it is.
yeah. So okay.
Yeah.
So
Yeah,
the
but it really
wavelength
does depend on
is the frequency?
It's the
Yeah.
frequency, not the intensity.
Oh, okay.
That's the only
So the
bad
higher
one.
the frequency, the more electrons that come off.
And that's what we discovered
And
from
that's what
the
you said earlier.
photoelectric.
I know.
You just messed it up just now.
Yeah.
I just got confused with my own word.
Okay.
Hey guys, I think we're done.
Yeah, I think we should probably
Alright, goodbye.
close out.
Okay.
All right, bye.
Roll rocks.
From Carl.
Peace out.
Goodbye.